All right, so in the previous video, we found the Maclaurin series for the sine function. It seems natural that the next thing we want to do is look at the Maclaurin series for the cosine function, and we follow a similar pattern. So if I find some derivatives of the cosine function, f of x is cosine of x, f prime of x is negative sine of x, f double prime, negative cosine of x, f triple prime is sine of x, and then by the time we get to the fourth derivative, we are now repeating this pattern. We're back to cosine of x again. Okay, as before, because we're looking at a Maclaurin series, I want to plug zeros in for these x's. So what is f of 0? What is f prime of 0? F double prime and so on. Okay, so every time I encounter a sign, like here and here, we already know that that's going to give us zeros. Cosine of 0 is 1. Negative cosine of 0 would be negative 1. Here's another cosine, so I get a 1. I have a similar pattern as what was occurring with the sine function, but now it's the other derivatives that I'm getting 0. It's the odd ordered derivatives that are coming out to 0, and the even ordered derivatives are coming out to plus or minus 1. So what this tells me is that my Maclaurin series for cosine of x is equal to my constant term 1 plus 0, so there's no x term. My second order term, which gives me my x squared term, looks like minus 1 over 2 factorial x squared plus 0, so no x cubed term, plus 1, positive this time, over 4 factorial, because it's my fourth derivative here, x to the fourth. And what we're seeing is a similar pattern, alternating pluses and minuses, and I'm only getting my even powered terms. So because I had a plus here, I'm anticipating a minus here, 1 over 6 factorial x to the sixth, and then plus, I'll get an 8th degree term. It just continues on. If I want to put this in summation notation, I'm going to do something similar to what I did for the sine function. I have this alternating plus and minus pattern, so I'm going to have negative 1 to the n. Notice this would give me a positive first term since n is equal to 0 first. And then we said this is equal to x to a power over a factorial, and the number that I'm taking the factorial of will match that exponent on my x each time. So whatever I put up here, I'm going to put it down here and then take the factorial. This time I'm looking at even powers. So 2 to the power of, or 2n would give me even numbers. And does it give me the correct even numbers? Well, when n is equal to 0, this would be x to the 0, which is just 1, giving me that constant term. When n is equal to 1, this becomes x squared. So my next term is, in fact, x squared. This will give me the correct terms. So I have 2n here. I'm going to have 2n factorial down here. Be careful to put the 2n in parentheses. If I just wrote 2n factorial without parentheses, the literal meaning of that is 2 times n factorial, which is different from this. So the parentheses really matter right there. That's the Maclaurin series for the cosine function. I can prove that cosine is equal to its Maclaurin series, but the proof would be almost identical to what we did for the sine function, so it's not worth going through that. We're just going to take advantage of the assumption that these two things are equal to each other. All right, so far all of our examples that we've worked through have been Maclaurin series. We haven't done any Taylor series centered at a different value. So we're going to still look at f of x equals cosine of x, but we're going to find a Taylor series centered at something other than 0. In particular, I want it to be centered at pi over 4. Okay, so we still start off the same way as the previous example. I'm finding a bunch of derivatives, and as before, it's helpful to go all the way to the fourth derivative because that's where we see a pattern emerging for this particular function. So I'm starting with cosine of x, then I'll have negative sine of x here, negative cosine there, sine of x, and then back to cosine of x here. Okay, here's where this example will look different from the previous one. In the previous example, because I was looking at a Maclaurin series, I was plugging zeros in for x's, my x's here. Now I'm plugging pi over 4's in. So what I want is f of pi over 4, f prime of pi over 4, f double prime of pi over 4, and so on and so forth. And as before, we're going to go all the way down to our fourth derivative for this guy. Okay, so cosine and sine of pi over 4 are both equal to root 2 over 2. So these are going to look like a bunch of root 2 over 2's, some of which will have a negative in front. So root 2 over 2, negative root 2 over 2, negative root 2 over 2, root 2 over 2, root 2 over 2. Okay? So what is the Taylor series going to look like? Well, not only do we have different coefficients, but we have to also remember that we're not looking at x and x squared and x cubed and all that. We're looking at x minus pi over 4 to each of those powers, because this Taylor series is centered at pi over 4. So my Taylor series is going to look like this. Cosine of x is equal to my constant term, root 2 over 2, plus this coefficient right here, so minus root 2 over 2x minus pi over 4. I have a minus for my second degree term, so minus root 2 over 2. Remember, this is over 2 factorial. X minus pi over 4 squared. And then my third degree term is positive, so I'm going to have plus root 2 over 2 over 3 factorial x minus pi over 4 cubed plus root 2 over 2 over 4 factorial x minus pi over 4 to the 4th power plus dot dot dot. And actually my next term would be a minus, but that's fine. So I'm not going to worry about putting this one in summation notation. That's not always necessary. It's helpful sometimes, but for this I'm okay just leaving this in this form. So the purpose of this example is to show you how finding a series centered at something other than 0 differs from when we find a Maclaurin series. Starts the same way, but we plug different numbers into these derivatives here, and then we're also having x minus that thing that we're centering our power series at to a power instead of just x to a power. Okay, so pretty good. Now what I want to do is make a little catalog of some Taylor series or Maclaurin series in particular for common functions that we've already come up with. So in this section, we found these three Maclaurin series right here. E to the x, sine of x, cosine of x. All of these should look familiar. We just did those. In the previous section, we used this power series representation a lot. 1 over 1 minus x is equal to this power series right here. And then from this, and using some differentiation and integration theorems for power series, we came up with a power series for the inverse tangent function as well as natural log of 1 plus x. All of these are Maclaurin series because they're all centered at 0. And if you recall, at the beginning of this section, I stated that a power series representation for a function is unique. So for example, this function right here, I didn't come up with this power series by using the technique of this section. I didn't find derivatives of this thing and plug zeros into those derivatives and then use the formula for coming up with the coefficients of a Taylor series. We did this using a different technique. But because I came up with a power series representation for this function, I can already know that the Maclaurin series for this would be the exact same power series. I don't need to go through the work of evaluating that in a different way. Okay, now what's kind of cool is that once we've come up with this catalog of a few, Maclaurin series for basic functions, we can come up with Maclaurin series for more complicated functions just by using some algebraic manipulation. So for example, if I wanted to find the Maclaurin series for this function, f of x equals x squared times sine of x, that would be difficult to do directly, because remember, we need to find the first several derivatives of this function until a pattern emerges. But this we would need to use the product rule on over and over again, and that gets really complicated. So rather than doing that, I'm going to use the fact that sine of x already has a known Maclaurin series. And I'm just going to write this. X squared times sine of x is equal to x squared times the Maclaurin series for sine of x, which remember looked like this. Negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Now, that x squared does not depend on this n right here. So as far as this expression here is concerned, that x squared can be treated kind of like a constant. And I can multiply it in and combine it with this x to the 2n plus 1 that's already there. I would be adding their exponents, and I would get this. X to the 2n plus 3 over 2n plus 1 factorial. Took almost no work to do that. So I didn't need to go through that process of finding that really complicated set of derivatives and plugging numbers in and all of that kind of stuff. I just was able to multiply x squared directly into the power series that we already have. If I wanted to write out the first few terms of this, I can evaluate this, using the summation, or I can just come up here and I can think this is what sine of x would normally look like as a Maclaurin series, and I'm just multiplying each one of these terms by an x squared. So in other words, just adding 2 to each exponent. That would be like x cubed minus x to the 5th over 3 factorial plus x to the 7th over 5 factorial minus ... just goes on. Okay? Let's see if we can do that for something similar. So I want to find the Maclaurin series for f of x equals the natural log of 1 plus 8x cubed. Notice that this is the same thing as the natural log of 1 plus 2x quantity cubed. That's the same thing as this. But if I compare this to this function right here, then I'm looking at the natural log of 1 plus x, and I'm substituting this 2x cubed in for it. In fact, now that I think about it, we don't even need to have it in this form. It's actually fine to just leave it as an 8x cubed. So basically what I'm doing is I'm taking that 8x cubed and I'm substituting it in for the x here, which would simultaneously mean that I substituted in for all of the x's here. Okay, so that tells me that the natural log of 1 plus 8x cubed is just equal to this power series, n equals 0 to infinity. The natural log of 1 plus x had this form to it, so it's an alternating series. Negative 1 to the n minus 1, or n plus 1 accomplishes the same thing. Negative 1, I'm going to say n plus 1 just because I like that a little bit more, times, normally it's x to the n over n, but I'm replacing that x with an 8x cubed. 8x cubed to the power of n over n. Okay, I'm not even going to bother writing out some new terms or a few terms for that. This is going to be sufficient. So notice there was one step. I just made a substitution in a power series that I already found. So that's where this gets really useful, because even though there's only a handful of Maclaurin series here, I can get a ton of new Maclaurin series using algebraic manipulations on these. Okay? Okay. Next step, this example is something that we have talked about previously, and we just said that we can't prove it yet, but we can show it now. So we want to show that the sum of the alternating harmonic series is equal to the natural log of 2. Now, if you remember when we talked about the alternating harmonic series a while back, when we talked about the fact that it converges conditionally, we showed that you can rearrange the terms of the alternating harmonic series and get a different sum. What this is referring to is the alternating harmonic series with no rearrangement of those terms. So remember, the alternating harmonic series looks like this. It's a sum where n goes from 0 to infinity of negative 1 to the n times 1, where you don't even need to write times 1, but over n. That's how we define the alternating harmonic series. But you can write this way. Negative 1 to the n times 1 to the n. Of course, 1 to the n is just 1, so it doesn't really change anything when I do that. But my reasoning for doing that is because I can now compare this to the Maclaurin series for the natural log of 1 plus x. Notice it's the same form, but the x here is a 1 here. So by plugging a 1 in for that x, I could alternatively just plug a 1 in for the x that this Maclaurin series is equal to, and that gives me its sum. This is equal to the natural log of 1 plus 1, or natural log of 2. Notice there was almost no work to actually do there. Super straightforward, okay? All right, I'm looking at my next example, and I see that I had a printer error here, so there was more here, and for some reason it didn't print correctly. I think, oh yeah, the only thing that was missing is that this was a cosine of x, so it's just missing a couple of letters, I guess. This is a limit problem, and it's a limit problem that we don't actually need Taylor series and Maclaurin series to be able to do. We can evaluate this using L'Hopital's rule. It would take a couple of applications of it, but it's not a hard one to do. The purpose of this example is to show you that Maclaurin series for functions gives you an alternative approach to evaluating limits of this type. So first of all, if you try to evaluate this limit using direct substitution by plugging 0 in for all of the x's, you're going to get a 0 over 0. This is 1 minus cosine of x over 1 plus x minus e to the x. That would be 0 over 0. So what I'm going to do here is I'm going to, instead of going straight to L'Hopital's rule, which would apply, I'm going to take that e to the x and that cosine of x, and I'm going to write their Maclaurin series. So we're looking at 1 minus, now the Maclaurin series for cosine of x, I'm not going to use summation notation. I'm going to write out the first few terms. 1 plus x squared over 2 factorial. Minus, that's a minus right there. Plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial, and so on, plus dot, dot, dot. Okay? In my denominator, I have 1 plus x minus e to the x, but e to the x has a Maclaurin series that looks like this. 1 plus x squared over 2 plus x cubed over 3 plus dot, 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 like that. Okay? Now, if you notice, when I distribute this minus sign in up here, I have 1 minus 1. Those 1's cancel. And then the minus will change the signs of all of these remaining terms. So now I have a positive x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, and so on. Down here, I have a 1 plus x, but then the first two terms that I'm subtracting are another 1 plus x. So those will cancel with those. The minus will come and change all of those signs. Now I have negative x squared over 2 factorial minus x cubed over 3 factorial minus x to the 4th over 4 factorial, and so on. Okay, so now I can evaluate this limit as x goes to 0 of this power series over a power series. And you might be looking at that and thinking, it still doesn't seem to help very much, because if I use direct substitution, I still get 0 over 0. But the trick here is to notice that I have my lowest degree term in both my numerator and denominator is an x squared term. So what I'm going to do is multiply my numerator and denominator by 1 over x squared. 1 over x squared over 1 over x squared. It's like multiplying it by a 1. What that's going to do for me is it's going to cancel an x squared from each term. So I get 1 over 2 factorial minus x squared over 4 factorial plus dot, dot, dot. And then here I'm going to get negative 1 over 2 factorial minus x over 3 factorial minus dot, dot, dot. All of these remaining terms will still have x's in them. And if I take x to 0, if I let the x go to 0, then all of the terms that still have x's in them will go to 0, leaving me with this constant over this constant. 1 over 2 factorial over negative 1 over 2 factorial is just negative 1. Okay? So Maclaurin series gave us a method for finding the limit of that function. Again, L'Hopital's rule would have also worked, but it's just an alternative approach. Another example, and this one's a little bit more interesting. The integral of e to the x squared dx. I want to evaluate this antiderivative as an infinite series. The reason this is an interesting example is because e to the power of x squared is a famous function for the fact that it does not have an antiderivative that you can represent using elementary functions. It's a fancy way of saying that this function is resistant to the fundamental theorem of calculus. You actually cannot find a direct antiderivative for this using conventional means. So instead, if we change this integrand into its Maclaurin series, then we can integrate that Maclaurin series term by term. So I can do this, e to the x squared dx. I'm integrating that. What does this look like? Well, up here in parentheses, I have the Maclaurin series for e to the x, but I'm substituting x squared in for all of these x's. Notice that all that's going to really do is double the exponent on each of those x's. So I'm going to get the integral of 1 plus x squared now, plus x to the 4th over 2 factorial, plus x to the 6th over 3 factorial, and so on and so forth, dx. Now this is an indefinite integral, so I pick up a constant of integration, c, which I'm going to write first. And then when I integrate this term by term, my 1 becomes an x. Then I get plus x cubed over 3 factorial. Over, not 3 factorial, just over 3. Plus x to the 5th over 5 times the 2 factorial that was already there. Plus x to the 7th over 7 times the 3 factorial that was already there. And then there's a pattern that emerges, and we're just going to say dot, dot, dot to indicate that pattern. So the reason this is really cool is because not only does e to the x squared not have an antiderivative, but this integral in certain forms actually shows up in some really important applications. One of which is in statistics. We need to integrate a function that's very similar to this one, but you can't do it directly. By representing it as a power series, we get a power series representation for this antiderivative. And then if we need to get values for it, like if we were using a definite integral, we can just pick, whatever degree of our Taylor polynomial that we want to use as an approximation. So this is a way around the fact that we can't actually integrate this directly. Really useful. Okay. All right, just a couple more examples to talk about. I think I'm going to use one more video to do these.